There's one here. And there's actually two over here. I drew kind of a bad picture. Really, the picture should look more like this. Or something like this. It's sort of like four-sided figure. But I kind of drew these too close together because I'm bad at drawing. So my apologies for that. But there should be two corner points over here. There's one that's an intersection between the black line and the green line. And there's one that's an intersection between the red line and the green line. So I get 4 corner points. Okay. So you do need to be a little careful when you draw your graphs, but again, approximations are fine, or usually good enough. I will tell you, you guys are taking this class online, so you are allowed to use like calculators and stuff. So if you have a graphing calculator, or if you find one online that seems reasonable, you can check your work, I suppose is my point. It might make things a little easier, I don't know. You could fidget around with that. But anyway, I won't say any more about that. Let's move on with this. Let's find our corner points. So I don't have 4 corner points. Let's find out where they are. So how do we find corner points? So remember what I told you is that in general, if I want to find exactly the coordinates of the corner points, I need to solve a system of 2 equations. And I take the equations that come from the 2 lines that intersect at the corner point. Now, 2 of our corner points are sort of obvious. I know there's 0, 0. That's where x equals 0 and y equals 0 intersect, the red and the purple lines. So I know I have 0, 0. I also know that I have 0, 10, because that's the y-intercept of this purple line, and that's where it intersects with, sorry, it's the y-intercept of the black line, and it's intersecting the purple line, which was the y-axis. So I have 0, 10. So those 2 are sort of obvious. The other 2 seem less obvious. And that might just be because of how I drew the graph, but it might just be that they're actually not obvious. So we should solve for them to make sure. So let's solve for these 2. So there's the first one is the intersection of the red and the green. So the system that I would have to solve would be taking those equations. So the red equation was negative 6y equals 0. And the green equation was 4x, or I guess when I solved it out for you guys, it was y equals negative 2x plus 32. All right. So this is my red, and this is my green. Those are the 2 lines intersecting in a corner point. So I can solve this system of 2 equations, and it'll tell me the coordinates of the corner point. If negative 6y equals 0, what do I know? Well, I have to know then that y equals 0. So I automatically have y equals 0. That's good. And that should make sense because I'm on the x-axis where the y-coordinates are 0. And so now I'm just going to take y equals 0 and plug it in here and solve for x. So I have 0 equals negative 2x plus 32. If you solve this out by adding 2x to both sides and dividing by 2, I think we're going to get x equals 16. So just solve this equation for x. You should get x equals 16. So my other corner point is 16, 0. And I solved for that exactly. So maybe, if I had drawn this perfectly, I could have eyeballed that. It looks like I drew it really bad because it looks like it's about 20. So this goes to show you can't always trust your eyes. Sometimes you need to go in and solve it exactly to make sure that you're doing, that you have the right numbers. So don't rely on your eyes too much. That's my caution that I'll repeat for you guys. Always check, solve them out, make sure. Okay. So that's my third corner point. This is 16, 0. Finally, there's one more corner point, which says it's the intersection of the green and the black lines. And so the green was, again, y equals negative 2x plus 32. And the black was y equals negative 1/2 x plus 10. So now I have to solve this system of equations. And again, since I have them both solved for y, I'm just going to use substitution. I'm going to substitute one into the other. And so I'm going to get this equation, negative 2x plus 32 equals negative 1/2 x plus 10. And now I just need to solve this for x. So when I solve this for x, I don't know. There's a bunch of ways you guys could do this. I'll be sort of quick. You guys could solve this however you want. Maybe I'd multiply both sides by negative 2. 4x minus 64 equals x minus 20, and then subtract x from both sides, and maybe add 64 to both sides. And I think we get 3x equals 44, in which case x is 44 divided by 3, which is some number. That's some number, who knows, some number between 10 and 15. 44 divided by 3. This will not reduce any further, so we'll just write it that way. Okay, so that's my x coordinate. Now I would just need to plug this back into one of these equations to find the y coordinate. So maybe, y is equal to -2 times 44 over 3 plus 32. That's -88 over 3 plus, if I want to write 32 over 3, that's 96 over 3. So I think we just get 8 over 3 is y. So it looks like our last corner point is 44 over 3 and 8 over 3 are our coordinates. So here are our 4 corner points for this system of inequalities. So 0, 0, 0, 10, 16, 0, and 44 thirds and 8 thirds. Those are my 4 corner points. Okay, so like maybe if I had drawn my graph perfectly, I could find these 3 without really solving anything. But absolutely, I would need to solve for this one because I don't think you'd ever eyeball that from your picture, no matter how perfect it was. So we need to know how to solve for corner points mathematically like that. Again, we just take the 2 lines that intersect at that point, put their equations in a system of inequalities, and then we solve, or sorry, a system of equations, and then we solve that system of equations. Okay, so I will pause and ask if there are any questions. This is the end of this example. So. Okay. So I recommend, when you're doing these, try to do them by hand as much as possible. Do things like, if you need to, if you have big y-intercepts or something, changing the tick mark values is good, can be helpful. And also solving out your things into slope-intercept form is also very helpful. 1, it helps you graph, and 2, it makes solving these systems nice because you just substitute like this and then solve. So it kind of kills 2 birds with 1 stone. Anyway, this was a complicated example. I wanted to do one more complicated, both as a refresher and just to sort of show you some of these things. But now I think what I'm going to do is move into 7.3 material. So I'm going to do that. Basically what we're going to do now in 7.3 is begin applying this stuff to actually solving problems. Solving the linear programming style problems. So we're going to be finding maximums and minimums using systems of inequalities and such. So 7.3, I don't know, what do they call this in your book? I don't know. Anyway, I'm just going to call it solving linear programming problems. So if you remember in 7.1, that whole section was just setting up problems, but you guys never solved any of them. Now that we have tools from 7.2 about graphing inequalities and finding corner points, we can now start solving linear programming problems. And here's why. So just recall the ingredients of a linear programming problem. We have an objective function, which we usually denote by capital P. And again, this is something that that represents whatever we want to find the maximum or minimum of. So often it was like profit or cost or something like that, right? You might want to maximize profit or minimize cost or something like that. And so P is just some formula that represents whatever that quantity is that we want to maximize or minimize. We call it the objective function. And then we had constraints. And these were just a system of inequalities. So in linear programming, they get called constraints, but they were represented by a system of inequalities. So these were basically the ingredients for a linear programming problem. And I'll remind you that there were two types of constraints, but in the end, it didn't really matter a whole lot in the sense that they're both just inequalities. But there were explicit and implicit constraints. And explicit will be given to you explicitly in the problem, in the information of the problem. Implicit, you need to sort of include on your own. They're not given in the problem explicitly, but you have to include them to make the problem make sense. And usually the implicit ones just look like x is greater than or equal to 0 or y is greater than or equal to 0. So usually it's making your variables not negative so that they make sense. Because if it's like you're producing shirts, t-shirts or something, it doesn't make any sense to have a negative number of t-shirts. So I better have a non-negative variable representing the number of t-shirts. Okay, so these are our ingredients for any linear programming problem. And our goal is pretty much find max or min of P. And maybe the phrase I would say is find the minimum or maximum of P subject to these constraints. Okay. So why can we now solve these? Here's why. So here's a fact that I'm going to tell you. I'm not going to justify it in any way. So you're just going to have to take me on faith on this one. Which kind of happens a lot in this class, but that's okay. Here's our big fact. And there'll be another one related to this in a second. But here's our big fact. If the feasible set, so remember the feasible set is the fancy name for the solution to the system of inequalities. So the solution to the constraints as a system of inequalities is called the feasible set. If that feasible set is bounded, and so I told you guys about bounded feasible sets before. Remember, that just means that it makes a closed shape. So like, you know, something like this. You graph your feasible set and you get like a triangle, or you get a square or some four-sided polygon or whatever. You get some closed off shape. It does not go on forever. It's nice and some finite closed off shape. That's a bounded feasible set. I told you that we'd like bounded ones, and here's why. If the feasible set is bounded, then P, our objective function, has both a min and a max, and they happen at a corner point, or at corner points, I'll say. To illustrate that they're gonna, you know, the min and the max will probably happen at different spots, at different corner points. But they must happen at corner points. So if I give you an objective function and I give you a constraint and the feasible set is a bounded set, then the min and max of the objective function have to happen at corner points. So if I'm looking for the minimum or maximum of P and I have a bounded feasible set, then I only have to check P at the corner points, and that's it. So we only need to check at corner points. So remember that the objective function P is some formula with the variables x and y in it. Points in the plane have x and y coordinates. So when I say we need to check P at the corner points, I just mean plug in the coordinates of the corner points into the formula and see what you get. Okay. So this fact is what will allow us to solve linear programming problems. Again, I'm not going to prove this is true. I'm just going to tell you it's true, and hopefully you'll believe me that it is. I promise it's true. So this is good. This gives us a roadmap of what to do. So let me just outline the procedure, and then we'll do some examples.